year review for Standard 5, Transforming Functions. It would be a good idea to wait on this particular slideshow movie until you've studied multiple functions, but it's okay because you can probably figure things out even if you're not familiar with the function being used. So here we go, transforming functions. The first thing to think about is the vocabulary. There are three things we can do when we transform. We can translate. That's moving the graph without changing any of its shape or flipping it. It's just taking the graph, its existing picture, and picking it up and moving it, left, right, up, or down. A dilation is when we stretch or shrink the graph. We're not going to change where it sits. We're not going to move it sideways or up or down. And we're not going to flip it upside down. We're just going to take the whole thing and stretch it taller or shorter, wider or skinnier. Then we can reflect. Reflecting is flipping graphs, taking it and flipping it upside down or flipping it sideways. That's a reflection. We don't change where it sits per se, so we're not moving it left or right. It looks like it will move because of the nature of the reflection, but it really doesn't. And we're not changing the shape. It doesn't all of a sudden get taller or skinnier or anything because we reflect it. We can reflect over either of the axes, or if we want to get more interesting, we can reflect over various lines. So now the secret really is in the word itself. To transform does mean to change. If I want to transform a function rule, I have to change it in some way. So I was thinking about baking. I guess I was hungry when I was doing this. If I want to change a recipe, you don't just leave something out, and you don't just put anything else in. Each ingredient in a recipe is there for a reason, either for a flavor or for the chemical reaction it's going to cause. So just randomly changing things isn't going to make my recipe turn out. To change a recipe, I have to replace an ingredient with something else, like if I want to put butter instead of oil in a recipe. I can make that substitution across many different recipes because butter provides a fat similar to oil. It does the same job, it just shifts my recipe from one idea to another, but it should still come out in much the same way. With function rules, that's the same idea. If I want to make a particular transformation, I have to figure out which ingredient am I changing. Am I changing an X ingredient or a Y? You can think of the X as like a flavor ingredient and a Y as a chemical reaction. So if I want to change X, maybe I switch chocolate chips in a cookie to butterscotch chips, just shifting my recipe over to a new flavor. If I'm looking at Y, that would be like the butter and oil. If I'm making banana bread and I don't have any vegetable oil in my house, but I have butter, I could use that instead. So I'm shifting my ingredients to a designated substitute. So there are some rules as to what I'm allowed to change to. Like I wouldn't change oil into something like water. It just won't work. So let's look at each of the transformations one at a time. We'll start with translations. Now as we go through this video, please feel free to pause at any point in time and re-listen and re-look. Take time to process. So with a translation, I'm going to take you over here to Desmos. We're going to use absolute value of x. I feel like this is a really good function for seeing translation changes. That V shape makes it easy to spot. So we're going to come over here and look at the absolute value of x. And there it is. Now, I decided to change the absolute value by adding 2 inside to the x. Let's see what that does. Aha, that seemed to move the graph 2 to the left. Now, why would that make sense? We could memorize, 2 left means add 2. And if I changed this to 3 or 4 or 5, we'd see that pattern. But I want you guys to understand why a plus 2 goes to left. What it comes down to is looking at the two tables. When I shift this absolute value green V over to the purple V, none of the Y values changed. I just took an X of 1, which used to go to a height of 1, and I moved that height of 1 over to here, where X was negative 1. So when I'm thinking about that horizontal shift, the only thing that's changing table-wise are my x's. So the way for me to see what's really happening is I need to get my new table's x's to have the same 5 y values that I had to start. So let's see here. I have 0, 1, 2. That's these. So let me go down here and shift the table to get my 0, 1, 2. And then I'm just going to continue the pattern. So there, now my y's match. So my question is, this went 2 left. What would I have to do to the new x values to get back to the old? Oh. I would have to add 2 to the new x to get to the old x. Aha. Add 2 to the new x to get back to the same y values I had before. That's intriguing. Let's play with this in some other graphs. So here's x minus 3. We'll make it orange so we can see it better. Now if I look, what did this thing do? Looks like it moved 3 to the right. Once again, let's get the table reset so that it matches the y values, because it looks like all we did was a horizontal shift. So let's see here. 1, 2, there we go. Does that match my original table? Perfect. So now again, what would I have to do to my new x's to get back to my old x's? I'd have to subtract 3 from my new x to get back to the old. Subtract 3 from x. Okay. Let's look at this again. Here's a new graph. What did it do? This went up 1. Okay. Up means that my y values changed. So let's look and see if we can make the x's in the two tables match. Oh, they do. That's always nice. So now what do I have to do to the new y's to get back to the old y's? Subtract 1. Huh? Wait a second. Oh, but think about it. If I were to do this, like I'm saying, look at that. Subtract 1 from the new y. Looks like the graph is the same. It's just in the world of functions, we always like to solve for y. We like the y to be equal to everything. So we shift it over. Aha, now let's look at this one. This one did what we thought, down 2. So what would I have to do to my new y's to get back to my old y's? I'd have to add 2 to my new y's, which, if I were to rewrite it, that's what it would look like. So let's go back now and put this all together. So with translations, anytime I want to move, I got to think about which way. So if I'm moving up or down by k units, that means a vertical change. It's the y that changes. Moving up means I'm going to have to subtract that many from the new y. Moving down means I'd have to add that many to the new y to get back. So to do that change, I replace y with y minus k or y plus k. Same with the left-right shifting. Right means change x to x minus h. Left means change x to x plus h. So you're going to notice we're doing the opposite of what makes sense. In every case, it makes more sense to do what it says, like up means plus, right means plus. But instead, we're doing the opposite. So if we just keep that in mind, this all becomes easier. Let's look at this in action. I'm going to use x squared this time. Again, nice shape for seeing translations. So starting with x squared, my blue graph, to move 5 down means I change y to y plus 5, opposite of what I would think. So now I solve for y, and I get y equals x squared minus 5. And there it is, the red graph. Now you might think that that parabola got bigger. but it didn't. Remember that parabolas continue to expand outward, so their width is constantly increasing as they go up in this case. So think about if I took that red graph, look at this bowl right here at the bottom. Now look at the bowl of the original blue. That's the same width. It's just that in moving it down, I get to see a whole lot more of the upper, wider part of the parabola. Let's look at another one. How about moving 5 left? Moving 5 left is an x change. I do the opposite of what I would think, so change x to x plus 5, and I would get here. Now, I can leave it that way, or I could multiply it out if someone really wanted it in that form. I think leaving it in the parentheses form makes more sense because you can see the transformation. The x, which was being squared, got changed to an x plus 5, which is now being squared. And you can see the whole graph moved 5 left. So now let's go to dilations. Once again, we're going to use Desmos, and I'm going to use sine x because sine is a great function for seeing changes in height and width. So here's our sine function. Now I know I'm not working in radians or anything like that, so that might make things a little harder to see, but it's okay. Just look at the values. Here's my original sine function, and here's the original table. So let's look at what happens if I put a number in front. And let's give this a color so we can see it better. Let's go purple. This graph seems to have stretched, but if I look, every peak of the old graph is now just taller. So it used to be a peak of 1, now it's a peak of 3. And each valley just seems deeper. But all of these x-intercepts didn't change. They're in the same spot. So I didn't move it sideways. I didn't stretch it because stretching sideways would have pulled my x-intercepts. All I did was take every peak and valley and just stretch it up or down. This became 3 times taller. So taller means y. What would I have to do to this y value to get back to where it was before? Negative 2.7 to negative 0.9. Looks like I'm going to divide my new y by 3. And again, let's look at how that behaves. Dividing my new y by 3 looks the same. It's just that we don't like leaving it in that form. So we multiply both sides by 3, and we get our new function. Okay. Now this time, I went ahead and put a 2 in front of x. Oh, that's interesting. If you notice, none of the heights of the peaks and valleys have changed in any way. This is still at a height of 1. This is still dipping to negative 1. What has happened, though, is it looks like I've taken each of these x-intercepts. So like, here's the x-intercept that came after the first peak, and I've slid it over. Here's the x-intercept from the valley. It came way over here. So now, when I look at this sine graph, I have one copy of the sine graph, starting at 0 and going over here to about 6 point something. It now takes 1, 2 of the black graph to fill the same spot. That means that this got half as wide. That's shrinking by a half. But when we look, we say, what do I have to do to the original x's to get to the same values I had before? Well, here, an x of negative 1 got me my y of negative 0.9. Up here, it's an x of negative 2 that got me that same y value. So to get from the new to the old, I have to double the new x. Oh, double the new x. Okay, that makes sense. Now let's just look at a couple more. This one, if I solved for y, I'd have 4y equals sine x. So I'd have to multiply every one of my new y's by 4 to get to my old y's. That would seem to indicate that this new graph's going to be shorter. Oh, goodness, yes, it is. Much shorter. How about this one? This one says I'm doing a third of x. So it's like saying, what do I have to do to each of these x's to get back to the original? Wow, it's even kind of hard to see because these y's got so tiny that to try to match them up kind of makes me think that this thing got really wide. Yep, every single x on this graph, you'd have to cut it to bring it back. And so what would I have to do to each of these x's to get back to those y's? I'd have to do the 1/3. And it's hard to see, but if I came up here, let's make this one -1/3, just so you can see it. If I take 1/3 of my new x, that gets me the same y value that I had up here. So kind of hard to see, but it's there. So when I look at that, it gives me my dilations, which I'm starting to think is doing the same thing. If I want to make it taller, I'm dividing y by something. If I want to make it shorter, I'm multiplying y by something. Because in every case I'm saying, what do you want me to do to the new y's to get back to the old? If the new y is taller, I'd have to cut it to get back to the old. If the new y is shorter, I'd have to make it bigger to get back to the old. If the new x is wider, I'd have to cut it to get back to the old x. If the new x is shorter, I'd have to multiply it, make it bigger to get back to the old x. So once again, we're doing the opposite of what makes sense. Let's see it in action. This time I'm going to use cosine. Cosine's way more fun, very similar to sine. Let's say I want to stretch it by a factor of 4 taller. Well, if I want it 4 times taller, I change y to y divided by 4, because I'm going to have to divide each new y by 4. I substitute and I solve for y. And now I have, whoops, this should have been blue. Let's make that a little bit better. Change our color scheme so it's proper. There we go. My original graph is now 4 times taller. All right. So now let's take a look here. Shrink horizontally by a factor of 1/3. So I want my graph to be 1/3 as wide as it used to be. That means that every new x would have to be tripled to get back to the old. So I'm going to change x to 3x. So here's my original cosine in blue. Now here's 3x. Well, you'll notice let's see here. If I look at my cosine going from this valley to this valley, 1, 2, 3 green fit in the same peak of the original cosine. So one full peak wave takes 3 now. So of course the green graph is 3 times as skinny, I guess, 1/3 the width. So now let's go look at reflections. Reflections are another tricky one. They can be easy, they can be hard. But let's go look at log x. It's another good shape for seeing. So here's my log graph. Kind of interesting. Shoots down there, shoots across. Let's take a look now at putting a negative in front. You'll notice my green graph looks like every single y value just flipped. No matter where I was on x, it went from having positive above the x-axis to being negative. This looks like an x-axis reflection, which we know changes y. So what would I have to do to each y value here to get back to its original? It's technically divide the y by -1. I suppose we could say multiply, because with -1 it makes no difference. but we're doing divide the new y by -1. So if we look at that, that's what it would have looked like originally. But then again, we always like to solve for y. And so we get to here. What about this one? That looks like a y-axis reflection. And it looks like we're doing the same thing. We're dividing the new x by -1, which gives me -x. Okay. But now let's look at reflecting over something different. So what if I want to reflect over the line y equals 2? Now, to reflect over y equals 2 means that every one of these points treats the purple line as the mirror, and it just flips over to the other side. So this point would flip over to here, this would flip over to there, all the way down to this x-intercept, which is at 0, 1, 2 units away from purple line, would have to flip to 2 units above. So this x value went from a height of 0 to a height of 4. Interesting. Now, we know that this is going to be a vertical reflection. We know that's y. So I'm going to change y to y, -y. All right, let's do this. So I'm going to change y to -y and solve. And then we get here. That's not a reflection over that line. I need this green graph now to move up. How far do I need it to move up? Well, it's at a height of 1, 0. That's 2. I need it to be at 4. So I need it to move up 4. So then I have to change y to y minus 4. And I solve and I get here. Now let's go back and look at what I really did. If I kind of reverse engineer this, so subtract that 4 over, and then I have to divide by -1. This is what I get. So reflecting over the line y equals 2 got me -y plus 4. 4. I wonder. If it were at 3, that wasn't enough. 5? No. 6. Ah, that green is a reflection over purple. So now if I backtrack, -y plus 6. So if this were 5, would this be 10? Interesting. So now what if I wanted to do something like the line x equals 5? Now, if I'm reflecting over x equals 5, that's a different story. Now I want this x-intercept to come way over here. I don't want anything to change vertically. I want it to flip this way. Well, I know that if I'm doing a horizontal flip, I'm going to change x to -x. But now again comes my problem. Here was my intercept. This was at x equals 1. I need it to get over to the line 5, which is a space of 4. And then I need it to travel over 4 more to be at 9. Well, when I flip the graph around, it's at -1. I need it to travel all the way over to 9. That means I need it to move 10 spaces to the right. Not there. Interesting. 10 to the right. That seems a little strange. Now, what if this were only 2? Now, with the y, it seemed to be twice as much. And it looks like it's doing the same thing. I wonder what would happen if I put in -3. So should that be 6? No. Oh, -6. That becomes very interesting. Let's go back. So when I do regular reflections, I'm just changing y and x to their negatives. When I want to reflect over a line, it seems like all of a sudden it's gone back to being what makes sense. The reason why is to think about factoring. If I were doing this by factoring, here is that shift. If I'm going to positive k, minus 2k is that up. The reflection negates all of that. Same with this. If I were to factor it out, positive h would be to the right. There's my minus 2h. So we're doing the opposites. Everything's opposite, including this is the opposite of what I thought the opposite should be. So I add. Seems kind of strange, huh? So now let's take a look. I'm going to get rid of Desmos here. We don't need this anymore. Let's pull this over so we can see it bigger. I'm going to start with an exponential function. So 2 to the x. If I just want to do an x-axis reflection, I change y to negative y. I solve, and there we go. The original 2 to the x, there's the reflected form. So far, so good. Let's try a y-axis reflection. There's the original 2 to the x in red. Change x to negative x, there's not much else to do. And there it is, flipped over that y-axis. Now what if I wanted to do over the line y equals 3? Well, we know that we're going to change y, because y equals 3 is going to be a vertical reflection, that I'm going to change y to negative y plus 2 times the line. So I'm going to change it to negative y plus 6. All right, so I subtract 6. Now when I divide by negative 1, that becomes negative 2 to the x. That becomes plus 6. And there it is. How about reflecting over this vertical line, x equals 2? So I'm going to change x to negative x plus 2 times the line, or negative x plus 4. Now this is easy, I just toss it in and I'm done. And there it is. So now it's time to put it all together. Let's take a look at multiple transformations and put it all into one. So here's the thing to remember. The order in which you apply transformations does matter because they follow the rules for order of operations. So you do have to make sure that when you apply multiple transformations, you should make the transformation by swapping what you need to swap and then do any simplifying you can before you do something else. That will make it work and everything will turn out the way it needs to turn out. So this works for every function. I could do this with a good old-fashioned mx plus b. I can do it with a trig function. No matter what, if it's a function, these rules apply. So it goes across so many different families. So now let's do a different family. We're going to use the inverse or rational function, y equals 1 over x. So let's say I want to move it 3 left. I'm going to swap the x to x plus 3, and there it is. So my original is in black. There it is. The whole thing just slid over 3 to the left. Now let's take that graph that I slid to the left and make it twice as tall. So I know I'm swapping y to y over 2. So there I made the change. I took the original function, I did the swap. Then to get rid of divide by 2, I multiplied by 2. And of course, when you multiply a fraction by 2, you just double its numerator. So now the blue graph has been stretched. Every x is now twice as tall as it was before. All right, I'm going to delete some of the old graphs now so that we can see. Again, black is the original. So now I'm going to take 2 over x plus 3, which was that blue graph, and I'm going to shrink it horizontally by 1/4. So I'm going to shrink it in. That means I'm going to swap x to 4x. So I did it, and I get here. You'll notice that now where the green graph seems to be sort of contained by x equals 1, whereas before the blue graph was contained over here by x equals -3. So now it's x equals -1, sorry. That seems to be that asymptote. So I've brought everything in. Now if I wanted to take that green graph and reflect it over the y-axis, so take everything here, oops, not the y-axis, that's the x-axis. I would swap the y to -y. There we go. And I'd work it through. So I would change it out, work the negative, and you'll notice each green point just flipped across the axis to get to the purple. And now if I wanted to go 5 down, I'm going to take that purple graph and move it 5 spaces down. So I swap y to y plus 5. And so, as I look at this whole set of transformations, here's the final graph with all the different colors. I started with black, 1 over x. Then I moved it 3 left to red, made it twice as tall to blue, then shrunk it in by 1/4 to green, then flipped it over to purple, and then moved it down to orange. And there is my final rule. This is the nature of transformations. The best thing you can do for yourself is to make up problems for yourself, try it, and use Desmos as a way to chart and follow each transformation to see if it does what it should do. That's the best way you can handle transformations. Good luck and try some practice.